Thank you, Julie, for that very generous introduction, and thank you to Dr. Jones and to the rest of you for inviting me here today. I'm going to talk about something that's been very interconnected at a high level with the work that we've done with ONR over the years. And it's really about sort of the intersection of advanced materials and what goes on in materials at the mesoscale. And so to start, I should probably define some of these terms. And so advanced materials, if I just sort of look at in my backyard, just around Santa Barbara, there are things like 3D printed ceramic lattices, semiconductors at the root of all the IR cameras that we use. One of my former students just made all the new materials for the Apple Watch. I can stand on my deck and watch the SpaceX guys send their rockets up. One of our graduate students has started a company with plant-derived coatings that increases the shelf life of fruits and vegetables by many, many weeks. We have stents, we have Tesla up the street. We can talk about the batteries, not the software, but there are many, many different places where advanced materials show up, and there are many opportunities for them. There might be many more if we were faster at understanding and developing these materials. So advanced materials, but what about the mesoscale? And so let me sort of step through the length scales in a way that hopefully everyone here will arrive at the same place with me. So we can start at the system scale, and I sort of define that as being sort of the meter to 350 meters or so. And so here is a system that I presume everyone here is familiar with, so the aircraft carrier. And these are remarkable vehicles with any number of interesting and amazing materials problems. We have aircraft sitting on the deck there. Those 17.1 meters in length. This is a F-18, I believe. I once got the chance to go to the Naval Air Station and do the flight simulator for this when I was working at GE. And I crashed 4 F-18s in the space of less than 3 minutes. So good thing I wasn't a pilot. You'll notice this afterburner here. So there's engines at the back. And this is the GE engine that sits in that system, which actually many, many years ago I had some role in, and particularly the materials in the hot part of this engine. So this is the system scale. Systems are, of course, very complicated, require lots of engineering across the disciplines, and materials being one of those. Now, if we go to the opposite end of the spectrum to the atomic scale, this is a place within material science and physics where there's been tremendous progress in the last decade or two. And it's to the point now with the ability to use density functional theory to calculate properties of finite numbers of collections of atoms. We can now, as you can see here, have cells. This one happens to be 32 atoms in size. And so we can begin to look at materials that are multi-component, which has always been one of the challenges with density functional theory. Small cells, you can't put the right atoms in there. And so we're learning tremendous amounts at this end of the spectrum. And we're also able to put this together with other techniques to calculate properties of materials at finite temperatures. At the same time, there's been tremendous developments in characterization at the atomic scale, so atom probes and high-resolution transmission electron microscopes. And so you can see the structure here of a perfect crystal and an image where the bright spots are representative of the location of individual atoms. And so while there has been tremendous progress, the challenge here is that even probably the best DoD computers can still only do a DFT calculation for perhaps 1 million atoms. And in the absence of really being able to calculate everything, what one does is impose periodic boundary conditions. And so what this means is that if you're going to do a calculation at the atomic scale and try to apply it to the macro scale, you have a problem, because in just a cubic centimeter of aluminum, you have about 10 to the 24 atoms, and you have only 1 million atoms to work with in calculating it. And so there are still gaps, and so I guess I'm still a little bit skeptical when we talk about going directly from atoms to airplanes, because we still haven't gotten the cubic centimeter together yet. So there's still things to do at the length scales in between. And so if you just go back to this image of the perfect lattice and just look over a region that's a little bit larger, I won't dwell on the details, but you can actually see there's some disturbance here. And so there are defects very close by, and almost always there are defects. And so defects are, of course, part of the problem with trying to predict how any given material will act. And so these defects in the crystal structure typically exist at the nanoscale and have implications for what goes on at other scales. If we step up to the microscale, so maybe 0.2 of a micron to 100 microns, this is sort of the traditional domain of all the early material science and engineering. And what I show here is, well, now we've got 2 elements, but thermodynamically, those 2 elements wish to form 2 different crystal structures. And this is really sort of at the root of all of the work that people have done to strengthen materials. And so we find out ways to control the mixtures of elements such that we form multiple phases, and we control their distribution and size. And that's how we get steel and nickel-based alloys and titanium, and there are also analogs in polymers where you have basically mixes of phases that allow you to control properties. And so if this is all we really had to predict, we might be in reasonably good shape, but there's more. So as you step up in scale, now if you look here, these are sort of maybe 0.5 micron, and so we're stepping out. And so, right, if you really zoomed in here, you'd see those little cubes, but you can see there's, as you zoom out, a superstructure in this material and many materials, which has to do with the way the material is manufactured. And so even though at a very fine scale it may look very uniform, as you get more coarse, there might be chemical segregation. You were looking at individual crystals earlier, but the crystals form independently of one another and come together as a polycrystalline structure. And so then you have a disturbance at the boundary at each one of these places. And so this is most materials are polycrystalline in character, and so there's a lot of things to worry about with regard to controlling and characterizing that structure. And so these things matter. I've chosen one little example here because it's such a topic that everyone seems interested in. If you now take, say, titanium or nickel or something like that into an additive manufacturing process, so now you've changed the structure of the individual crystals here, and you can see, well, maybe you didn't scan the laser right, so there's some powder particles there, and there's an associated disturbance with the structure and so forth. And so not only do we have defects that sort of come as an intrinsic part of the process, but also we have interactions with the environment. So there may be things going on at the surface, oxides forming while you're using the material, or there may be internal things that found their way into the material, which one has to sort of account for in either a probabilistic way or a more deterministic way with models. And so the picture here is that there are many length scales to take care of, but the one that we are still struggling with the most from the point of view of being able to go all the way from atomistics to macroscopic structures is sort of here in the mesoscale, so sort of the 50 to 100 microns to the centimeter scale. And of course, this is very closely related to the components because in many cases, these things exist almost at the same scale. And then you superimpose maybe a coating and some other things to mitigate some of the environment. And so it becomes necessary to have big suites of models that can pass information from one to the next to figure out how to relate the mesoscale to the component scale. And so I show here again that engine from earlier. I'm going to talk a little bit about some of the stuff in the hot section just as an example. This is a turbine disc, so this is probably the most safety critical thing in the engine. If you lose it, you lose probably the plane in most instances. Okay, so coming back to the mesoscale, typically what we have to do is sort of account for all of that structure. And to design systems, of course, we need properties of the material. So there's this intimate connection between those features of the material that you saw and any number of properties that you might use to design something. So if thermal expansion is your concern, then maybe you can predict that from density functional theory and first principles, and we might be in pretty good shape there. If you want to know something about permeability or how strength or toughness or even worse, fatigue, what you find is that the sort of representative volume element that you need to be sure that you're describing in detail goes up in scale. And so inevitably for some of these properties that are important from the point of view of structures, we end up again sort of at this mesoscale. And so this is one of the subjects that sort of motivated aspects of the Materials Genome Initiative. And it's this inability to predict all of these things when you have a new material that slows us down. So we have always new materials in our laboratories that we think would be great for someone to use because it has some specific property that's interesting, but one of those other properties on the chart will stand in your way. And so the whole idea is that we should build an infrastructure where we can at least speed this up by twice as much and maybe take some of the cost out just because we can be more predictive. And so the idea is that you can't just compute everything, but you have to bring together correct suites of computational, experimental, and data tools. And that if you do that in a way that you drive the understanding and development of the materials with modeling rather than just measuring what happens to be convenient to measure, then this should help us take advantage of some of the new materials that we find in our laboratories. Okay, so focusing a little bit on how are we going to get that information quickly at the mesoscale so we can use it and drive the models that let us predict the way the materials will behave. A number of years back when the discussions about all of this were starting, it was apparent, one, that I guess if I haven't said it, these things all exist in 3D. So taking a 2D section is typically not good enough because of the geometrical complexity of the materials and as well as the defects in them. And so it immediately brought attention to the tomography techniques. And materials as a field is perhaps a bit behind our colleagues in medicine and other areas with tomography. And if you took a close look a few years back at what was available, of course, we had new atom probes coming online, which was quite exciting. You could get volumetric information in new ways down at sort of the nanometer cube scale. Transmission electron microscopes, again, way down at the small scale. There's been tremendous evolution in synchrotron beamlines. Unfortunately, if you don't have one in your backyard, you may only get the chance to do that experiment once, maybe twice a year. There were some mechanical approaches to sectioning things, and then there was the focused ion beam microscope platform, which lives at the micron scale. So there weren't too many things out here in the cubic millimeter scale that would serve to quickly acquire that information, particularly for materials which are pretty dense and not very always so amenable to these approaches. So we decided, with the support of ONR, to go after this business of tomography aided by femtosecond lasers. And in the end, the motivation here is that tomography, of course, is slice by slice removal of material. And so what we had to do was understand whether or not it would be possible. Many, many people told us it was not possible, even after we did it. But the idea here was that you could remove material layer by layer 1,000,000 times faster than you could with the focused ion beam. So why? Well, with femtosecond lasers, this is some unpublished MD simulations that George Gilmer's done. And based on a lot of experiments, we believe this picture to be fairly true. So the special thing about a femtosecond laser is you have an incoming pulse, and it is only, in the case of the lasers that we're using, there for 150 femtoseconds. So you're really only interacting with the electronic system. By the time these electrons are excited and rain back down on the material to launch a shock wave, which launches a small layer of bladed material, the beam is gone. And so if the pulse were longer, this material would be coming off, and you'd be dumping a lot of energy into the ablatant that's trying to come off the surface. But because it's not, this 50 nanometer or so layer can be launched off the surface with, while maintaining a liquid-like state rather than a plasma state. And so what that allows you to do is take 50 nanometers at a time off very, very quickly, doing very little collateral damage to the material under it. The other the other thing that's interesting about this, if you look at ablation rate versus fluence, so just the focused intensity of the laser, we're always, because it's a Gaussian beam, we're always using the edge of the beam. And it turns out that almost all materials sort of act in a similar way at low fluences. And so that suggested to us before we started that this would be a fairly materials blind approach, which is good because most of these other techniques certainly have narrow slices of classes of materials that will work. Okay, so here's what we did. We sort of brought together a femtosecond laser with a focused ion beam microscope platform. So this part of it is a commercial platform. We've had a very good collaboration with the microscope manufacturer, who's actually given us a microscope to build up the second and third version of this. But anyway, what you want to do is couple the laser mechanically and, of course, optically with the electron beam and the ion beam that already exist. And then we have detectors, one, an EBSD detector, which gives us crystal orientation information, an ion beam, which we can use for very small amounts of material removal. We use that sometimes we don't. And then the electron beam, which will allow us to gather structural information. And then we also have over here an EDS detector, which gives us chemical information. So we can get structure, chemistry, orientation, and then use all of that information to understand the material. So here's what it looks like at the present. So all of the laser things are boxed up here, and then they go into the microscope here, and then the rest of it looks like a pretty normal focused ion beam platform. This is the unit that goes to collect the crystallographic information, and so we've been teaching instrument manufacturers lots of things about fatigue, because this goes in and out and in and out every time we make a slice. And so that's how the system works. This is what it looks like inside. So the laser beam's here, electron beam, and the ion beam and EBSD over here. So it's a little crowded in there, and that sets the size of the system that we can look at. There's a piezoelectric stage which sets the slice thickness. Okay, so how's this work? Here is a material that we came upon as a result of a hypersonic theory with Julie. And this material is a copper tungsten composite. It's used, I think, I'm not supposed to know, so I guess it's used in high heat flux conditions, I think mostly for ballast, but what you're supposed to be able to do is ablate the copper out to save the material. And so the question is, if you have this composite, what's the conductivity of the copper, and how will that be able to cool the tungsten by ablating out? And so we picked this material because copper and tungsten are very different. We thought it would be a good test of whether or not the system works. So this was one of our early experiments. And so what we're always doing is taking the laser beam like this and scanning over the surface of the sample. And so if the beam has a Gaussian profile, that means we're just using the edge of the Gaussian profile. Yes, somebody's texting me, sorry about that. And so this is a typical workflow. So we're usually sort of knocking off, maybe a few square millimeters. So we set up the sample. The slicing, unlike many other techniques, where the business of preparing the layer takes a long time. This is just sort of a few seconds, up to 25 seconds. You may use the FIB to clean up a little bit. Then you image, and you get chemical and crystallographic data. So depending on what you want, the time per slice will vary. But it could be as little as sort of about a minute per slice if you're not trying to gather crystallographic information. And so this is a data set after it's been sliced and reconstructed. And you can see the composite and each of the phases here. And this took about 30 hours to gather. And you can see there's really very good resolution. I think I forgot to show you. So this is what it looks like as you're slicing. So you can see the material's being ablated, but you're not destroying the surface structure of the material, and so there's no further preparation. So you're just removing it and imaging it as you go along. And so you can see voids appearing here and the shapes of the copper changing as we go along. Okay, so it turns out that we do have this ability to gather a lot of data. So immediately a bunch of questions come up. How much data do you need? What are you going to do with it? How predictive can you be? And also, what can you measure that you couldn't measure before? So in this case, we're worried about the permeability of that copper, so it can ablate out. And so one could just use an analytical model as a start. And there are many models for permeability, and the reason there's so many models is that you can't usually measure surface area per unit volume. So if you can, then you could just do something simple like Cosine and Fermin. And so here I show two different volume fractions of that copper, and the important point is we can measure this quantity, the volume fraction or the surface area per unit volume. We can measure it in the whole data set, or we can measure it in subsamples of the data set, and in that way begin to sort of develop a statistical sense of what is the represented volume element. How big does the data set need to be to predict a property with a certain degree of confidence? And so you can see here these blue bars basically show you when the microstructural features converge and when the properties converge. And so in this case, we had gathered more data than we needed. And so one of the things we'd like to be able to do is, on the fly reconstruction and calculation. And that's not as easy as it sounds. Okay, now, of course, if you don't think the analytical model is good enough, you can mesh and actually do fluid flow calculations, which we have done. And in this particular case, this is a simple enough material that those things give you similar answers. Okay, so I don't want to dwell on this, but because this technique's fairly blind to different classes of materials, and because you can gather a lot of data, we sort of really have begun to quiz people when they come and ask us for a data set. Well, why do you need it? And so I think if you don't know why you need it, and you can't pre-calculate how large it is, because many of these data sets, if you set up the experiment, can quickly rise to 20 gigabytes and approach a terabyte, depending on what information you save. And then you can't even open it up in your computer and do anything with it. So we have a lot of questions that we ask. And what are you trying to do? Well, you're usually trying to measure, quantify, or observe, gather statistical information of the sort that I just showed you. Or maybe you need this as validation for some model, or you need to know what volume of material is relevant to a given property. So I'll just give a couple examples of that. So here is a titanium material, titanium 6 aluminum 4 vanadium. If you've ever ridden a bicycle or had anything made out of titanium, it was probably this material. And this 3D data set here, oh wow, I've lost the scale. This is about 500 microns along here. This color here gives you a sense of there's clusters of grains of similar orientations. This turns out to be a problem, and I won't dwell on why it's a problem, but it's something that people worry about if they're relying on titanium in safety critical environments. And so this is a fairly complex structure that we've sampled here. And so instead of trying to take this very complex structure and apply a surface and volume mesh to it, this is a collaborative work we have with a program with Bill Mullins and Cornell. So instead of doing that, you can analyze this data set, take out all the distributions of the sizes and orientations of the grains, and now make a virtual sample. Just sample from the distribution and reconstruct a virtual sample. And that way, you can do more parametric studies of what the importance of certain things are, and make virtual samples that are representative of what you've measured here. And so I show here some simulations for how this material actually fails. And what you can see is that this presence or absence of these clusters of grains strongly influences the failure process. And so, again, that was always one of these things that was very hard to predict without this kind of information. Other uses for this, this is a synchrotron sample. And very often in the synchrotron, you miss small features. And so this was an experiment to try to understand how the structure evolved. Very precious sample that 2 years was invested in doing these experiments. But they needed to know what was missing. So we took the sample and then developed some techniques for comparing these. And again, that's not so easy because all detectors have different distortions, and you have to develop sort of rigorous mathematical routines to automatically bring these data sets together. Because when you have thousands and millions of features, you can no longer do anything manually. And so here's the difference. Here's the things that we found. There are 159 features, grains, in our data set that they didn't find. And there were a few they found that we didn't find, and that had to do with sort of how you put a criterion on how to call a boundary. So here's one other sort of example from that list of reasons why you would do this. This is a Thermoelectric, which is obviously of interest for harvesting waste heat. These Heusler intermetallic compounds are interesting because their figure of merit peaks in sort of the range of temperatures where most automotive or turbine engine exhausts would be exhausting air. And so the idea here is to combine these two structurally similar crystal structures to get lots of boundaries so that we can lower the thermal conductivity. Well, the problem quickly becomes is that you cannot distinguish the diffraction patterns, and so you have to have some other mode of distinguishing the two phases. So you need, in this case, chemical information as well as crystallographic information. And you need it in 3 dimensions to actually get the interfacial area. And so this just shows the distribution of all the different kinds of interfaces in the material. And this is useful for trying to predict thermal conductivity. All right, one more example. Going back to our aircraft engine, this is the turbine disc, the safety critical thing. You don't really need to know any of these details other than these are kind of complicated nickel alloys. And they are polycrystalline in character. They have these special features in the grains known as twins, so it's just a special crystallographic orientation to the material around it, and they're highly elastically anisotropic. So people who make aircraft engines have been working on these things for decades to remove all of the extrinsic defects because you don't want any crack growth to go on in these if you can help it. And so there is usually when these fail in laboratory tests, they don't actually fail at any kind of extrinsic defect. The failures just initiate within the structure. And so the question is, what in this structure is the reason that a crack would initiate? And if I knew exactly why it did, then I could probably change the process, I could make better models, so on and so forth. And so this is probably the material we've gathered the most data for to date because it's being used by a number of people to try to work on some of those predictions. And so I won't talk about the details, but there's a lot of interesting things you need to do, which is, well, you need to develop algorithms to define those special boundaries. And it's very easy to see them, and it's a little bit harder with a voxelized data set to precisely define them, but we developed some ways to do that. And so these red boundaries turn out to be the twin boundaries, and they are associated with the processes that initially start a crack. And so we've done many experiments to sort of flag all the features beyond associated with that structure, as well as the other features intrinsic to the material that matter. And so this is kind of a list of them: the misorientation between boundaries, those twins, the orientation with regard to the stresses, how the material is deforming, the lengths of the boundaries, and then the mismatch on either side of these boundaries. And so I don't think you have to worry about the details, but the point here is that we can now actually go and get statistically significant information about what matters in these volumes of materials. And so in this data set, what we've done is gone through and applied all those criteria and asked ourselves, now, what are we left with in terms of eligible initiation sites? And so we start out with 68,545 boundaries here. And when we apply all of those criteria that we know are individually important to the entire data set, we basically end up with only 146 initiation boundaries that qualify for initiation. And so there is a bit of understanding about how you might change the processing of this material to chase some of those out. And then the other question is, there's a lot of life prediction methodology that one would want to do with these. And so the question is, again, how big of a chunk of material do I have to have in order to predict that I will have at least one of these initiation sites in my volume of material that I'm modeling. And so in this case, again, it comes out to about 475 microns. So again, we're back to that mesoscale size, and yet we're down to these very nanoscale processes. And so I think we finally have some ways of chasing these things. Now, so we're not the only people that are interested in that data. And so we would very much like to share it, and I'll show you a couple of cases where people have taken this, or some of these data sets. This is just a conventional test that we do in the lab, a fatigue test. You just cycle the material until cracks initiate, except we're watching very carefully. So a crack initiates here, and then we go and get a 3D data set around that. And then that gets passed off to General Electric. And because they don't really have good analytical models for these sorts of things, the idea is to mesh every feature of the material and then do a crystal plasticity calculation. And so this mesh is too big to be opened up anywhere but the supercomputer. And they've applied the crystal plasticity laws, and they do actually, even for the simple laws, seem to be identifying regions that are consistent with what we're seeing in terms of cracks being there. So their idea is that they would use this partly to design new materials, but also partly to predict how they'll behave in service. Here's another group doing the same thing, but in a bit more targeted way with more sophisticated crystal plasticity models. This is actually an Air Force program. I see Ali Sayer here. We're working with Johns Hopkins on that project, and this is Somnath Ghosh is modeling. And again, we have a 3D data set that they can take and mesh and then apply their models. This meshing business is pretty difficult, and there's still many problems to be solved there. Okay, so just to give you a sense of, I've shown you a few materials, but back to what I said about ablation, there are many different classes of materials that will work in this system. You'll see, for example, here we have a copper polymer composite. You don't see the 3D volume because we're generating data faster than we can reconstruct it in many of these cases. And so we have been able to generate lots of data sets, but many of the challenges come in dealing with the data and getting from the slice data to the 3D data. And I think many people don't realize that there's a lot of challenges here because you have to do this rigorously and you have to do it in the computer because there's no doing reconstruction. Well, you can do it manually, but you'd need an army of undergraduates, I guess. But so there's routines that you have to develop for the collection, which you've seen the collection. But then there's all these things you have to do to really correct for distortions in the instruments, line the slices up, make sure that all the data's good, threshold the features, and remove the artifacts, and then finally reconstruct the data set. And then you want to be able to do analysis on the data set. And so again, there's another whole set of algorithms that have to be written. And so in the materials community, this now seems to be going on sort of in groups more than collectively, say, as maybe the medical community has done. And so we're trying to improve on that situation. So there's a couple of developments. At the Air Force, the Air Force has sort of been helping this small software company, Blue Quartz. And so they basically have put together a system where you can develop workflows to operate on the data set and keep a record of the workflow. And so at least for yourself, there's some record keeping, but that doesn't really do much for sharing all the algorithms that you've developed for a given material. And so we've actually managed, finally, to catch the attention of some of our computer science colleagues at Santa Barbara. And this particular set of people actually has developed the software platform for plant biology and all the imaging they do. And so we're now in the midst of a little experiment trying to turn this plant biology platform into a materials platform. Seems like an efficient way to get there. But this is basically a web-based thing that serves for analysis, visualization. And by annotation, I mean any information that comes from any of the instruments in the data set basically automatically is annotated, and that way you build automated databases. And then, of course, you can share it with people. So everyone can be doing their own calculations on the data set. So we're hopeful that we'll go from this serial, do this, go to another program, look at it, come back, change one parameter, so on and so forth, that they can actually now import these routines, do some parallelized computations across parameters, and then allow you to arrive at these reconstructed things much more quickly, and also allow you to share those workflows with other people. So hopefully what this means is that all these terabytes of data will be useful to someone other than just us. Okay, one last thought, and then I'll wrap up. I think these tools, combined with other sort of high throughput tools, will hopefully get us to the point of exploring the rest of compositional space. And what I mean by that is, you saw that nickel alloy, right? There are about 10 elements in it. Never mind the details of this, but if you can always ask yourself, what happens if I mix 3 elements together? And this is a ternary phase diagram. And right in the middle of this diagram, there's a new compound that appears when you mix things in certain proportions. And so cobalt, aluminum, tungsten, very common elements that we've been using for things forever. Well, we only found this phase a few years ago. And then a few months ago, in a 5-element system, somewhere in the middle of this composition phase, another useful phase was found. And so I think they're in the center of these compositional spaces. There's probably a lot that we don't know. And the question is, can we get there quickly to explore the composition space and help us find these new and potentially useful materials. So the way I kind of see it as well, we're getting good at printing. We're making powders of all sorts, so we should be able to dream up some nice ways of printing small samples. We could then take them to these automated 3D characterization platforms, look for new things, and compare to what is known in the emerging databases for the density functional theory calculations, which are at 0K. So you would have some guidance about how to work your way through space. And then, other high throughput properties, and gradually with these software platforms, build up the information. And well, if you find something interesting, then go print it and test it. So I think it's sort of an exciting time for materials at the mesoscale. There's lots of exciting things going on in materials, certainly at the nanoscale, 2D oxides and all kinds of other things. But I guess the message here is there's still plenty of things to do at this scale too. So with that, I'll wrap up. As I said, I think mesoscale phenomena often limit the use and performance of materials. There are lots of new tools coming together, and the community is working on these, and I've shown you one that we've in particular been working on, and I think that it will help us in the future to not only discover things, but hopefully to get things into engineering systems faster. So with that, thank you.